Hey everyone, Mr. Fransky here again. Today we're going to talk about the end of 3.7, which is finding the second derivative implicitly when we have x's and y's in the same function. This is going to be especially important in Chapter 4 when we start talking about concavity. And for now, just have faith that it's important for if we had like a particle that wasn't following a path that's a function, we might have to know something about the acceleration. So let's take a look. All right. So d squared y dx squared, remember that means the second derivative. And this process is actually pretty simple. If you understand the implicit differentiation, it's not going to be too bad at all. So to find the second derivative, as normal, we're probably going to have to find the first derivative first. So I'm going to do the derivative of the left side and the right side here. So derivative of the left side with respect to x, 6x squared, right? 3 comes to the front. And then it'll be minus, it'll be 6y, and then got to change, so multiply by y prime. Remember, because y is a function of x. So you should have an f of x, we don't know what it is, so we have to change by multiplying by y prime, equal to 0. So now we'll solve for y prime. I'm just going to add 6y, y prime to both sides. So we'll have 6x squared equal to 6y, y prime. And then if you divide by 6y, we end up with y prime equal to x squared over y. There we go. Okay, so we have our first derivative. Now, second derivative. Second derivative, we're just going to do the derivative of both sides here. Derivative of y prime, y double prime. We have a division. You may have noticed that usually when you do the derivative of a function like this implicitly, the last step is always division. So this is probably going to require quotient rule. Okay, so you're probably going to have to do quotient rule, because you probably did a division to get that y prime by itself. So we're going to do low d high, y times 2x, minus high d low, 2x times y prime, because the derivative of the bottom is just y prime, over the square of low we go, which is y squared. Now, this is correct, but we have a y prime here, okay? So probably use quotient rule, and you can have no y prime in your answer. Only x's and y's. So only x and y. So y prime, well, I don't know what that is, but, oh wait, I do. It's right here, right? So anytime you have a y prime in your answer, you're just going to substitute in whatever the derivative is. So this is going to be 2xy, I'll write that as, minus 2x times x squared over y divided by y. You can just leave it like that, right? That's just fine. And we're going to evaluate it at the point 1, 2, so as long as you can plug in the points, okay, you're good. We could, if we wanted to, make this like negative 2x cubed. We could slide this up on the top, negative 2x cubed over y, and then make a common denominator and get the y to the bottom. I'm not going to do that, though. I'm just going to evaluate this at the point they asked for. So evaluate this at the point 1, 2. Well, 1, 2. Erase all that. So if we plug in 1, 2, we're going to get 2 times 1 times 2, which is 2 times, I'll write it out, 2 times 1 times 2, minus 2 times 1 times 1/2, divided by 2. So it looks like that is 4 minus 1. 2 over 2 is 1, yep, divided by 2. Looks like 3/2. So for now, this value doesn't mean a lot to us, right? The slope of a tangent line would be over here. This doesn't really mean a whole lot to us right now, but being able to go through this process is important, and we will learn more about why that is later. All right, so you now have the worksheet has 4 examples on it where they ask you to find the second derivative, and it has the process at the top there. Just remember, take that first derivative, take the second derivative, which will probably be quotient rule, substitute in any y primes that you need to, and then simplify. So there is some sneaky algebra on, especially the last two, number 3 and number 4, have kind of a sneaky algebra trick to be able to simplify them to the end. But if you can go through the process we just used, that'll work just fine. So I'm going to go through those problems. If you'd like to follow along with me, you can. If you've gotten enough, then you are all done in less than 5 minutes. What a deal. You can try those problems on your own, and that key is online. But let's take a look at these. So we got sine x plus cosine y equals 1. So we derive both sides. Derivative of sine x is cosine x. Derivative of cosine y is negative, so right, negative sine y. And then we got to take care of the baby function, so we got to multiply by y prime, and that's equal to 0. If we add sine y, y prime to both sides, we have cosine x equals sine y, y prime. And then divide by sine y, we have y prime is equal to cosine x over sine y. Now you might say, hey, that's cotangent. Well, no, because it's x on the top and y on the bottom, right? So be careful. So second derivative is going to be low d high. So we have sine y times derivative of the top, which is negative sine x, minus high d low. So we have minus cosine x times cosine y over the square of low we go, which is, oh, did I do something wrong? I missed a chain rule somewhere. Low d high is good, minus high d low, so we need a y prime right there, over the square of low we go, which is sine squared y. Now we substitute in for that y prime, which I almost forgot. So we have sine y. I'm going to write this as negative sine x sine y. I'll do the x's first always. It just looks good to me. It's alphabetical order, right? Minus, we'll have cosine x cosine y times y prime, which is cosine x over sine y, divided by sine squared y. Now, of course, you can always just leave it like that, but my simplification bone is twitching. So let's see here. We have cosine y over sine y right here, right? Cosine y divided by sine y. That's tangent y. So you could write it like this. Negative sine x sine y minus, we have cosine squared x tangent y divided by sine squared y. You could even try to split this up and get some more stuff going on, like you have a sine y here that would cancel if you split it up. That sine y could come to the bottom and make a sine cubed out of the tangent. Lots of ways you could write that, but I think that's kind of the cleanest way to write it. I like that. Moving right along. So this time we're actually going to evaluate this at y equals 3. So first we should probably get a point, because we're going to need the x. So if y is 3, we're going to have 3x plus 9. Is that right? Yep, equal to 9. So if you subtract 9, 3x equals 0. Looks like x has to be 0. Okay, so our point is 0, 3. So we'll use that when we do second derivative. So let's find the first derivative, product rule. 1 times y plus x y prime plus 2y equal to 0. Get that y prime by itself, so we have xy prime equal to negative 2y minus y again, huh? Oh, I missed a y prime. Fransky, come on. 2y, y prime. There we go. So now if we factor out a y prime, we have y prime times x plus 2y equal to negative y. Now we divide. So we have y prime equal to negative y divided by x plus 2y. Okay, so there's our y prime. Now we'll get our y double prime. Low d high, x plus 2y times negative y prime, derivative of the top, negative y prime, minus high d low. So that'll actually be plus a y times 1 plus 2y prime, derivative of the bottom is 1 plus 2y prime. Over the square low we go, x plus 2y quantity squared. Now you have two choices here. We can put this in for y prime there and y prime there, but since we're evaluating it at the point 0, 3, we can also just plug those numbers in here and then use them. So we're going to evaluate this at 0, 3. So y prime, I can either put the function in and then plug in the numbers, which would be the same thing as plugging in the numbers first and then putting them in. So let's do that. So if we evaluate y prime at 0, 3, that's going to give me negative 3 divided by 0 plus 6. Looks like that is a negative 1/2. So I'm going to put negative 1/2 in for those two y primes, then 0 and 3 in for all the x's and y's. So we're going to have 0 plus 2y, which is 6. We'll have 6 times the opposite of y prime, which is 1/2, plus y, which is 3, times 1 plus 2y prime. 2y prime is a negative 1, so that's 0. Over the square of low we go, so x is 0, 2y is 6 squared. So it looks like we have 3 out of 36, which reduces to 1/12. All right, moving right along. So these last two have some sneaky algebra, and let's see what happens. So the derivative left here is 2x plus 2y y prime equal to 0. Solve for y prime. We'll have 2y y prime equal to negative 2x. Divide by 2y. Y prime is the opposite of x over y. So our second derivative then, y double prime, low d high, y times negative 1, minus high d low, negative x times y prime, over the square low we go, y squared. So that gives us a negative y plus x times y prime, which is negative x over y squared. Could leave it right there, but I'm going to show you something cool. So we have negative y minus x squared over y divided by y squared. I'm going to get a common denominator on the top, so I'm going to make this y squared over y. So now we have negative y squared minus x squared over y, and I'm going to slide that off, so we have multiplied by 1 over y squared. I'm going to factor out a negative from the top and come over here. So we have negative x squared plus y squared divided by y cubed. Now x squared plus y squared, we have a formula for that. It's 25. So this is actually negative 25 divided by y cubed. How simple of a second derivative is that? Took some weird algebra. You might have to go back and watch that process again of how I kind of factored out the negative after finding a common denominator. And I said, well, x squared plus y squared is always 25. We have that relationship in this function, or in this graph, so that's always got to be true. One of the interesting things here is that x squared plus y squared equals 25. That would be a circle centered at 0 with a radius of 5, right? Sure, you all knew that. And the second derivative, we haven't talked about this a lot, but it somehow has to do with acceleration. So if you imagine a particle marching along the outside of this circle, you may have learned this in physics. The acceleration is always to the inside of the circle, and it only depends on what the y-coordinate of the particle is. So that's why we can reduce this down to a function that only involves y. Kind of cool. All right, got one more that also has some funky algebra. So if you want to try it and see if you can make that algebra work out, you can. I'm just going to jump in. So we have 2x plus 8y y prime equal to 0. Get that y prime by itself, so I have 8y y prime equal to negative 2x. Divide by 8y, y prime is negative x over 4y. Is that right? I think I did that right. I hope so. So now we do the second derivative. Low d high. So I'll assume the negatives with the x on the top. You could also pull it to the front and just have it out there, but I find it's nice to attach to a function. So low d high, so we have 4y times negative 1 minus high d low, so we'll have plus x plus x times the derivative of the bottom, which is 4y prime. Over the square low we go, 16y squared. Replace that y prime with our negative x over 4y. So we're going to have negative 4y minus, let's see, so we put that 4, the 4's are going to cancel. Let's write that out. So x times 4 times negative x over 4y. So the 4's cancel. I'm holding the negative out to the front. So it'll be minus x squared over y divided by 16y squared. Now again, that's good enough. I am going to do a little bit more sneaky algebra. So make this a y squared over y. Combine those. So what do we have? We have the opposite of x squared plus 4y squared divided by y times 1 over 16y squared. This, once again, hey, it's 1. So this is equal to negative 1 over 16y cubed. Awesome. That's all there is to second derivatives with implicit differentiation. It's a little tricky, but the more practice you get, the better you'll get at it. It's not too bad. Love you guys. That's why I'm here. Have an excellent day.